Today, our guest speaker is Dr. Jean-Christophe Marongiu from the ANDRITZ Hydro Industrial Company. He works there as head of the Research and Development Department, located in Vevey, Switzerland. He has been driving the development of an in-house SPH-based software package to simulate water flows and support the design of hydraulic turbines. I should mention that Dr. Marongiu recently stepped down from the SPHERIC steering committee, where he was one of the longest serving members, and he played a particularly important role as a representative of the industry. And today, Dr. Marongiu will talk about SPH-ALE, a variant of the weakly compressible SPH approach. Dr. Marongiu will guide us through the applications of the SPH formulation in the modeling of hydraulic turbines. As usual, the format of the seminar is that we'll have this presentation, and then this will be followed by a Q&A. So I invite you to prepare your questions and post them in the chat, or if you want, just raise your hand and you'll be able to directly ask a question to Dr. Marongiu. So I guess without further ado, Jean-Christophe, the floor is yours. Thank you.
Okay, thank you very much. I will start by sharing my screen. And please, Angelo, confirm that it is well received
yes,
by everyone.
I can see. Yep,
you have it.
You.
Okay, yes. Very good. So thank you to Angelo and probably Ben and Nathan for giving me the opportunity to entertain you about an hour now on the usage of SPH methods in ANDRITZ Hydro for the purpose of simulating flows in hydraulic turbines. I will start briefly by introducing the company, ANDRITZ Hydro. So we belong to the global ANDRITZ group, which is an Austrian headquartered industrial company specialized in providing equipment for various industries. We are usually technology leaders in our markets, in our niche markets, with a lot of customization of the products for our customers. And we are listed on the Vienna Stock Exchange. Our activity weighs basically 6 billion euros per year, approximately. We have a global presence all around the world. And we are organized with 4 main divisions. The biggest and historical one in the group is the pulp and paper division, so providing equipment for the transformation of wood to paper, so the pulp and then the paper. So we provide turnkey paper mills all around the world. Another division is the metals division, whose activity is mainly composed of equipment for metal forming and especially for automotive industries. I belong to the hydro division, so we provide electromechanical equipment for hydropower generation, which is composed of turbines and hydro generators, among other products. And the last division is separation. We provide equipment for the solid liquid separation, dewatering, applications in wastewater treatments for municipalities, but also for various industries, including mining. So if we look at our products in ANDRITZ Hydro, here we have a schematic view of an hydropower plant with an upper and a lower reservoir, and in between you have a series of electromechanical equipment to transform the energy of water into electrical power. We do not provide the civil works, but we provide most of the equipment, what we call the water-to-wire approach, which is we provide gates, dam gates, stop logs and things like that, the pipings, the penstocks, the valves, the turbine, of course, the generators, which are low-speed generators because of low rotating speed of the turbines. All the control and protection equipment for that, down to the power transformation before sending the power to the transportation grid. Here you have the view of a nice pump power station in Germany, where you have an upper reservoir and a lower reservoir, which is directly the river. And this big building is the power plant. Because we have to adapt to the natural characteristics of every site that are equipped, there is a collection of various turbines, hydraulic turbines, to extract the maximum energy that we can out of a given site. And the sites, they are characterized by the difference of water levels between the upper and lower reservoir, what we call the head, the water head, H, and the water flow that will pass through the turbines. And so the power of a turbine is given by this formula and is mainly driven by those two parameters. And depending on this ratio between head and flow rate, we have all those various types of turbines, and we will focus more on this type of machines, the Pelton turbines, which are designed, or let's say specialized, for high head above a few hundred meters head and relatively low water flows. It's an old lady which was invented in the 19th century in California during the gold rush. Of course, we have worked quite a lot since then to improve its performance. So this is a modern looking Pelton runner here on the right. It is composed of, the runner itself is composed of many buckets. And the buckets, they will collect the energy of water. So if it is an action turbine where the energy, the pressure energy of water is transformed into a kinetic energy of a free surface jet, and the jet will impact the runner and transfer the energy. It's not a toy. We can deal with very big power levels. Here, for example, is the world record that is installed in the Swiss Alps. The water head is almost 2,000 meters. And a single runner, a single turbine can deliver up to 425 megawatts. And the plant is equipped with 3 similar units. So it's more than 1.2 gigawatt in this single power plant. This unit is composed of 5 jets. Okay, so it has a vertical shaft, 5 jets around the runner to increase the amount of water that a single runner can digest. We can also have horizontal axis machines, and machines can have from 1 to 6 jets for each runner. Here you can see that the runner diameter is almost 4 meters. When we look at the challenges for the investigations of the flow in these machines, we have to deal with quite complex physics. We have a combination of internal and free surface flows, internal in the Pelton distributor, and all those pipings upstream, internal flows. Then, of course, we have the jets and the runner. These are free surface flows. We have a rather complex geometry with rotating and static components. It's highly dynamic and unsteady. We have also very different time and length scales. Let's assume that the pipes, they are diameters of a few meters. The runner you have seen is also with a diameter of a few meters, but the buckets themselves, they are much smaller. And then in the jets, we have some surface perturbations with droplets. So it goes down to centimeters and millimeters. So hard to respect all the homologies, especially when we look at the model testing in laboratories. So we are equipped with our own hydraulic laboratory where we test small scale machines. This is the historical way to develop the hydraulic turbines, and it brought a lot of improvements in the past century, but it's also quite limited. It's of course very close to reality, but we have to sacrifice some of the homologies. It's quite expensive and slow in terms of development cycle time. And it only provides global information because of the free surface that hides basically what happens really on the rotating buckets. In the 90s, of course, the industry started to use major classical, I would say now, we call them classical now, CFD approaches using meshes, computational meshes, to investigate what happens. So it requires a tool that is able to represent a free surface with a mesh-based technique. Also, the free surface is generated in a non-rotating simulation domain, has to go across a rotor-stator mesh interface once at the entrance of the runner, but also a second time when the water exits from the runner and travels in the Pelton casing, in the turbine casing. And this is quite difficult. The mesh preparation is very tricky. The solver time is also quite expensive. A lot of expertise is required to set up such simulations. That's why at the beginning of 2003, the company started a research program aiming at making use of SPH-like tools to predict the free surface flows in Pelton turbines. So that's a bit the background and the introduction to today's talk. Now looking more precisely to the next steps, I will present what we have finally adopted as a numerical method to reach our target, which is the SPH Arbitrary Lagrange Eulerian approach. So I will give some details of what we manipulate. I will present a few corrections that we have added to this method and that we really use to reach good accuracy and precision of our simulations. Some extensions that are also paving the road for other type of applications, and finally some industrial applications in our for our hydraulic turbines, not only on the Pelton turbines, by the way. And in my conclusions, I will also let's say mention my opinion about the most demanding aspects of the method and where future investigations should focus on. So let's start with a bit of equations. Sorry for that, aiming at introducing the SPH-ALE approach. So I start not with SPH, but with conservation laws written in a moving frame of reference, arbitrary, I would say, moving frame of reference with this form. So it's quite a generic formulation where we can identify some important terms. The first one here, we speak about time derivatives along a certain trajectory, which is defined by a transport field that we will name V0 in our notations that can be chosen arbitrarily. Also, we will consider the conserved quantities described by a vector phi contained, I would say, in a moving control volume. Okay, that's a key ingredient. We will have a physical advection term. Usually the physical velocity field will be noted V, and V0 introduces a second advection term, which we will call the ALE advection. Then we have the source terms, surface and volume terms, and this notation here will be related to the surface of the control volume, the surface boundary of the control volume. This being said, we can have a more compact form, introducing a transport operator here, LV0, which is again defined by the transport velocity field V0. Then by rearranging those integrals, we have the divergence of the physical flux and an ALE flux. Okay, and if we apply that to 2D inviscid flows, the vector of conserved quantities is densities and the two momentum components. We have a physical flux function, which is with two components also here. And that depends again on velocity and density and pressure. It's not written, but I will consider that we compute the pressure with an equation of state like the Tate equation. So a barotropic equation of state. Now we jump to the discrete version. So thanks to Villa, we have an SPH-based discretization of this compact form here that has this form. So it's the time derivative of the conserved quantities where the volume of the particle appears and the numerical flusses which are summed over the neighborhood. So in terms of notations, I will usually designate the particle of interest, while J is related to the neighboring particles. And the neighboring particles, they are contained in a certain domain, which is noted di, and which is the support of the kernel function located on or centered on particle I. Here we have a numerical flux, which is adapted to a moving Riemann problem between the two particles I and J. And that one is used to solve the ordinary differential equation. Not solve, to assemble, sorry, the ordinary differential equation. So a few comments or a few details about this numerical flux. So let's take a very simplified neighborhood around particle I. Let's consider one of its neighbors with index J, and let's imagine that we have a sort of interface located between particle I and J, located at the middle point between the two particle centers. So position denoted xij, and the direction linking the two particle centers is noted nij. This numerical flux will be computed in the following manner. So let's start with the last line. We first compute the transport velocity at the interface point between particle I and J. For that, we take the transport velocity V0 here, and we project it on the unit unit vector linking particles I and J. We will use this velocity to look for a certain solution here at the interface between particle I and J, using a certain function that we will see later, but that will depend on this velocity, projected velocity, and on the two states. So the physical states on particle I and on particle J. Once we know the state here, so let's say that we know the density, the pressure, the velocity here at the interface between particle I and J, we use this interface state in the physical flux function. So we get the physical flux, and we also use it for the ALE flux. Again, with the interface velocity that is already used here to multiply the state. Okay, so that's how Villa instructs us how to compute the flux between the numerical flux between two interacting particles, I and J, in the ALE formulation. So some first properties, we have global conservation because this flux summation involves terms which are antisymmetric. Okay, so what is given from I to J is indeed received by J. Let's say it in a simple manner like that. But what it also shows is that there is a flux of mass between particles I and J. There is no reason to assume that this flux will be zero, which means that the mass of each particle will change during the simulation, which is a difference compared to the classical SPH approach. Of course, we need to add two equations to close the system, I would say. First is the motion of the particle centers. So obviously, in our case, we move them according the introduced transport velocity field. Okay, and we have a an additional equation compared to the classical SPH, which is an explicit time evolution equation for the volumes of each particle. It depends on the divergence of the transport velocity field. So the natural formulation is like that. It's equivalent to this one, where we introduce the interface velocity. We have seen that the physical flusses involve this interface velocity, and it's quite convenient for the rest of the method to have directly this interface velocity in the volume equation. This term involves symmetric contributions. It means the global volume is not conserved. That's a well-known feature in SPH. Here in SPH-ALE, it comes visible, I would say, in this equation for the volumes of each particle. Now, if we look at how we introduce boundary conditions in SPH-ALE, so we do that by using what I would call a modified gradient or divergence operator for the particles whose kernel support intersects the boundaries. In fact, it's just going back to the way we move usually the gradient operator from the function to the kernel function by integrating by parts, I would say. Usually what we do is that this term, the boundary contribution, is neglected because most of the particles are far enough from the boundary. So because also we usually have a compactly supported kernel function, this term is 0 for most of the particles in the domain. But for those particles which are close enough to the wall, which means at a distance which is less than the size of their kernel support, then there is a contribution that should not be neglected. And the approach we have followed is really to discretize that surface contribution in the gradient and divergence operators directly by discretizing the boundary surface with calculation points and applying a similar quadrature formula to take into account the flusses coming from the boundaries. So when we do that, we end up with a modified discrete conservation law where we have again the volume contributions that we had previously, where the summation is done over the neighbors, which are volumic particles, and the second sum, which is over the neighboring points, which are directly discretizing the surface, and they have a special extent, I would say, which is of one dimension lower than the problem dimension. Okay, so in 3D they are surfaces, and in 2D they are segments. We again have a numerical flux function that is adapted to a moving partial Riemann problem, because now instead of having two states, we have one state, which is the particle of interest, and the other state is in fact a boundary state. And at the boundary, we impose some part at least of the solution. We will see that later. And also in this summation, we no more have, of course, the kernel gradient. We have the kernel function and the normal vector at particle J, at surface element J. Now in practice, how do we compute the intermediate state that is at the heart of the numerical flusses? Well, we use Riemann solvers. The purpose of those solvers is to compute the solution of a discontinuous initial condition and for hyperbolic problems. If we restrict ourselves to the case of the Tate equation of state, we have only 4 states which are separated by 3 characteristic waves. So here we have a diagram with x, so it's in a one-dimensional approach, x being the space dimension and t being the time. Initially at t equals to 0, at x equals to 0, we have a discontinuity. On the left, we have a certain state characterized by its own density, velocity, and velocities, sorry. And on the right, the same, its own density and velocities. But then, right after t equals to 0, we start to develop at the interface new states characterized by a constant density, which means a constant pressure also in our case, a constant velocity in the direction of x. And if we are in 2 dimensions, the second velocity component is discontinuous on both sides of this third characteristic wave here that is in between the two of us. And the idea of Riemann solvers is to take as a solution at the interface, well, the solution that develops in these intermediate states. Okay, usually in classical, I would say, CFD approaches, the solution is sought along the characteristic direction x over t equals to 0, which corresponds to a steady Riemann problem. But here we have a moving Riemann problem because everything moves, and we look for the solution along the direction x over t equals to the lambda 0 that we were computing previously, so which is the projection of the transport velocity along the unit direction between particles I and j. Okay. So then to compute those states. So everything is determined as soon as we know the intermediate states here, rho star and v star. To do that, the exact solver requires an iterative procedure because we have something that is not linear, and it's quite expensive, and I would say it's a bit useless in our case because we have low Mach number flows and we are more or less in the linear domain. We don't suffer strong non-linearities. Accordingly, we can use linearized solvers, and here I have one form of such a linear solver where we see that the solution states, so rho star and v star, they are composed of what we call a centered contribution, which is an average between the left and right states, and then an upwinded contribution that depends on the discontinuity between left and right states. So the discontinuity in the velocity will influence the density, and the jump or discontinuity in density between left and right states will influence the velocity solution. Okay. And this upwinded part provides the required numerical viscosity or diffusion, if you want to call it like that, that is required to stabilize the numerical scheme, the overall numerical scheme. That is valid for the solution between two fluid states, particles, volume particles I and j. But if we have to deal with the contribution of a boundary, then we have a partial Riemann solver where, as I said previously, the imposed physical boundary condition already determines part of the solution of the Riemann problem. So now I adopt a different description. I take the diagram with the physical quantities, so velocity and density in our case, and I describe the states that the left state can reach following one of the characteristic waves depicted previously, and it can't reach any sort of states. It can only reach those states which belong to those characteristic lines, curves. So it gives a certain location of the solution. The second condition comes from the imposed physical boundary condition, as I said, that can be more or less easily described in this diagram. If we assume that we are at a subsonic inlet and we impose the velocity at the inlet, then the representation of the boundary condition is a vertical line in this diagram. And obviously, rho star and v star will be obtained by finding the intersection between all the states that can be reached from the left state following a characteristic curve and the imposed boundary condition. A second example, very similar, is the case of a subsonic outlet. Usually we impose a pressure. This is represented in our diagram by an horizontal line with constant density. Constant pressure, constant density is the same. And again, we can find the intersection. A slightly trickier configuration is if the case of a subsonic inlet where we want to impose a discharge. It means we want to impose a constant product of density and velocity. This can be represented by a curve, of course, in our diagram. And again, the solution will be the intersection between those two curves. In practice, how to solve for these partial Riemann solver is very similar to what was presented before. Especially, it's possible to use similar linearized solvers. They are not very expensive. They provide enough accuracy, and experience shows they are sufficient. Okay, so now we are equipped with a discrete form of the conservation laws, with the discrete forms also of the kinematic equations. We know how to solve the interface state between two interacting particles or between a particle and a boundary element, I would say, with a certain imposed physical boundary condition. So we have basically everything required to set up a complete system. I will not mention a lot what we use as a time integration, but we use explicit time integrations. Runge-Kutta schemes of second, third, or fourth order are good choices from our experience, and we simply use them. Okay, a bit of improvement in the frame of low Mach number flows. Those Riemann solvers presented just before, they tend to introduce an excessive, I would say, numerical viscosity. It's not only the case for low Mach number flows, also for medium Mach number flows, it's observed. And it's necessary to improve a little bit by adapting the states, left and right states, that we inject to the Riemann solver. To do that, a well-known technique, also derived from finite volumes, is called the muscle, where in fact the piecewise constant approximation, where we say that the left and right state, they correspond to the states at the particle centers I and j. They are replaced by linear extrapolations using a certain estimate for the field gradient on particle centers of I and j. So in practice, if we simply apply this extrapolation, we end up with left and right states, which are composed of the states at particle centers I and j, or j, and a certain extrapolation that depends on the gradient of the field estimated at particle I or particle j, and the distance, or let's say the vector joining particles I and j. If we just do that, the system tends to be unstable. That's also well known from the finite volumes experience. And it's necessary to introduce nonlinear functions, which are used as limiters to, let's say, cut the linear extrapolation from the center to the interface and respect some physical properties that already exist between the states at centers I and j. And those properties, they should also be found on the states reconstructed at the interface, so the left and right states. Okay, there is a huge literature on limiters for unstructured finite volumes, and our experience is that similar limiters can be used in SPH-ALE. There is not so much differences. Then it's more a question of computational cost or convenience of implementation when we have something highly unstructured like we have with the SPH neighborhood. Also, what we have implemented are non-reflecting open boundaries, so inlet and outlets. Those can be obtained with techniques like flux vector splitting and optimal linear relaxation to make sure that on long times, the attemptedly imposed physical boundary condition is indeed enforced, and there is not a major drift at minimum at convergence between what we try to impose and what is necessary with linear relaxation to prevent the reflection. So here I provide a simple example. It's a square in a domain with an inlet on the left, an outlet on the right. We impose inlet velocity, outlet pressure. We start from a domain which is more or less at rest. So we have transient waves at the beginning. And then what we want to prove, let's say, is whether we evacuate properly what appears in the domain, and what appears in the domain is a vortex shading. So this small square is very good at generating some flow perturbations. And the target here is to show that we evacuate properly those vortices without re-injecting major perturbations in the domain. And the same at the inlet. I don't provide more insight on this case, but obviously we monitor that the imposed velocity and pressures, they are maintained at convergence. Sorry. Okay, now that we have the basics, let's say, of SPH-ALE, we will have a look at some correction techniques that we have introduced. The first is balancing of the particle volumes. As I said, we have an explicit time evolution equation for the particle volumes that is based on the divergence of the transport velocity field. Let's assume that we choose this transport velocity field as being the physical velocity field, the Lagrangian field. We can have strong changes, I would say, from one part of the particle volumes, from one particle to the next one, because the regularity of the transport field plus the inaccuracies of the SPH divergence operator can lead to that. But we also know that SPH is not very good at playing with particles which have a different sizes. So our target here is to try to maintain a rather homogeneous map or field of particle volumes. And to achieve that, a certain diffusion term in the equation of the volumes is desirable. The choice we have made is to modify the transport velocity at the interface between interacting particles, between neighboring particles. This is very consistent with our numerical flusses. You remember this interface transport velocity is involved in the numerical flusses. So if we modify it, then it's also taken in account in the mass and momentum equations automatically. Okay, so that's why we have decided to play with this interface velocity. We will see later that there can be other reasons to play with that. But in practice, so we correct this interface velocity with a certain term that tries to distribute a small portion of the volume of the bigger particle to the smallest one. Okay, of course, pairwise. So when we have particle I and j interacting, One is certainly bigger than the other. And what we try to do is to transfer a small portion of the volume of the big particle to the small one. We apply a certain cutoff to that, not to transfer too much, and that's it. Yeah. And in practice, it reveals to be very efficient. It's almost inexpensive, but it's very efficient in maintaining the particles' volumes very close to the, let's say, target or initial value. Another correction is about, again, a modification of the Riemann solvers. As I said, even if we have muscle scheme, if we really have low Mach number flows, we suffer from a too high numerical diffusion, numerical viscosity. It's well known also in the finite volumes community. And a well-known solution on their side is to use preconditioning. So us, we have a sort of transient solver. And we don't want to compute steady state, converged steady state. We have to compute a succession of transient states. So the preconditioning can only be applied to the upwinded part of the Riemann solution. And in practice, it consists in multiplying the Riemann problem with a preconditioning matrix which scales with the Mach number, the square of the Mach number. So we take two linearized Riemann solvers, the so-called VF-rho scheme, so which is not with preconditioning, and the VF-rho Turkel scheme, which is with preconditioning. And you can see the difference in the case of a two-dimensional jet impacting a flat plate. Okay, so water or the liquid comes from above and is evacuating on both left and right sides. And you can see that the preconditioning is very efficient in reducing the numerical noise in the pressure field. I can also tell you that it's quite efficient in reducing the numerical viscosity. A drawback of that, well, it's not very expensive because even if we have to modify a little bit each and every Riemann solvers, I mean pairwise Riemann solutions, it's not very expensive, but it's expensive in the sense that with this highly reduced numerical viscosity, the stability is more demanding, and we have to use a smaller time step, a smaller CFL condition. So we increase a lot the number of iterations of the solver to reach a certain physical time. And this is a bit tricky. So in practice for industrial application, it's not always possible to pay that additional price. A more important issue is about how we do the flux summation in SPH, because SPH-ALE relies on a flux summation that is governed by SPH divergence operator. And we focus on what we in ANDRITZ call the closed box error and closed box correction. To introduce the topic, I make a parallel between finite volumes, integration stencils, and what we have in SPH. On the left, I have a sort of unstructured finite volume mesh that would be the closest variant of finite volumes to our SPH, I would say. And we know that by construction, the finite volume mesh fulfills this condition. At the continuous level, we expect that the integration of this term, which is the unit vector pointing outward the finite volume cell along the cell boundaries is equal to 0. And by construction, the finite volume mesh guarantees that very easily. Because let's say if we are in 2D with triangles, the triangles are real triangles. Okay. Now, if we look what we have also in 2D in SPH, well, at the continuous level, the equivalent to this condition here is supposedly fulfilled. But the discrete counterpart that involves maybe only volumic contributions or a combination of volumic and surfacic contributions, if our particle of interest is close enough to the boundaries, is not equal to 0 exactly. That's what we call the not closed box. Okay, and this is a problem. This is a problem because if we take a constant flux, like for example, a constant pressure field and particles at rest, with finite volumes, we would not create any sort of motion in the domain. While with SPH, all those terms which are not equal to 0, they mean that the constant pressure field will generate some momentum. And so we start to move the particles from iteration 2. Okay, and that's not what is expected. It's a very simple example of the problems we have with this error, but we have this error all the time, everywhere in the domain. So what we have tried, or what we have developed to combat this error is a correction of the kernel gradient that we put only on the volumic contributions, so on the contributions coming from the other SPH particles, not from the boundaries. We have modified the kernel gradient to distribute a certain portion of this error, which is a local error, to each and every volumic neighbor. Okay, so we have adopted a certain weighting that depends on the distance in the end. So closest neighbor and the other, they do not receive the same amount of correction, but in the end, this one here guarantees that we have a closed box, a sort of closed box. An illustration of how efficient it is, I take one example, which is Taylor-Green vortices on a steady particle distribution. So it's an Eulerian simulation. We take a Cartesian arrangement of the particles, initial arrangement of the particles that we slightly perturbed with a random noise. And we run the simulation. So at the bottom, you have what is provided as a solution by SPH-ALE. If we do not apply this correction, and you can see how noisy is the pressure field as a result of the random noise applied to the particle positions. On the top, we have the same, but applying this correction here, the closed box correction. And you can see that we manage to get back a very smooth pressure field similar to the one we obtain if we really use the original, I would say, or unperturbed Cartesian particle distribution. As I said, the error is local and the correction is local also, which means that we break the symmetry of interactions between particles I and J, which means that we break the global conservation. Here, it's the first time I introduced that. It's often a debate in the community whether we should favor conservation or consistency. Well, I tend to favor a little bit consistency in this situation because the benefit that we get in practical applications surpasses the drawback of breaking the global conservation. It's not the first time that we will do this choice, but here in the presentation, it's the first time. Okay. This correction technique that we apply on the kernel gradient so that we improve the flux summation scheme is related to the next one, which is the particle shifting. The previously introduced kernel correction cannot be used if the error that is monitored on a given particle becomes too large. I can't provide a precise meaning of what too large means, but I can tell that if we do nothing on the particle positions, we can't apply it for a very long time. So we have to maintain this error on a certain bound, on a certain range. And for that, so we apply a particle shifting, which is very highly inspired from the Palking algorithm that was introduced in the community by our Italian colleagues. We applied that particle shifting at each iteration by modifying the transport velocity of each particle. Okay, this is again very valid in our approach, ALE approach, to do that. Oh, how long do I have still?
Hi, Jean-Christophe. Yeah, you have between 5 to 10 minutes more.
Okay, I will hurry up a little bit. Okay, so this is the form of the correction, sorry. We have a certain number of particle motion modes. I will focus on one, which is what we call the Eulerian corrected. Here you can see that the correction involves also a possible motion of the boundary elements. Okay, and here is what we can see. We have moving NACA blades in 2 dimensions. Particles around those rearrange themselves according to this motion. The others, they remain steady. And we have no glitch, I would say, at the interface between moving. We have a smooth transition, in fact, between moving and steady particles. And here the same with blades, which are which have an open motion. So we establish a flow. It's the same. Particles around the blades here, they move. The others, they remain steady. And there is not an average motion from inlet to outlet. Okay. Okay, some extensions. Well, it's possible to have multiphase with SPH-ALE. For that, we block the convective flusses between interacting particles. And we also introduce acoustic Riemann solvers, which are able to derive a solution of the Riemann problem, even though we have a strong ratio of acoustic impedance, which means strong ratios of density, mainly. And here, as an example, is the collapse of a vapor bubble immersed in a heavy liquid, which is pressurized and close to a wall. And well, this is the results we have. So we have a microjet forming inside of the bubble during the collapse, and we can compute velocities and, more importantly, the pressure. Another extension is the coupling of SPH with finite volumes. The strategy relies on overlapping SPH and finite volume domains, and the target is to use each method where it is best suited, especially to have the neighborhood or the skin around a certain body managed by finite volumes, so that we can have refinement in the normal direction to the wall. We use chimera finite volume cells to transfer the information from the SPH domain to the finite volume domain. And the overlapped SPH particles, they can use finite volume cells as neighbors, or they can have their properties interpolated from the finite volume cells. And here you have a comparison, only SPH with a coarse particle distribution on the top. And below is a coupled simulation where we have this layer of finite volumes around the NACA airfoil. And this is much improved. And this is very close to the purely finite volume solutions. It can also run with moving bodies. Here we have a rigid body motion for the finite volume domain. And the particles, they rearrange themselves as previously using this Eulerian corrected motion mode. And here is an illustration of what it gives in terms of pressure predictions, with a clear motion of the stagnation point and the appearance of the detachment. Okay. Again, this coupling is not fully conservative, but consistency is for us more important. Another extension is with higher order schemes. here is to make sure that our overall SPH-ALE scheme is guaranteed to provide a certain convergence order, convergence rate everywhere in the domain. Necessary is to have higher order numerical flusses and flux summation operator. To do that, we used moving list squares. So for the numerical flusses, we replaced the muscle reconstruction with MLS reconstruction. And for the divergence operator, we replaced the SPH operator with MLS shape functions. This, by the way, naturally solved the closed box error issue. Some results here. It's again the case of a 2D jet impacting a flat plate. Here is the pressure coefficient in the domain. Here, the pressure coefficient on the plate. Here is the order that we reach with MLS in the domain. So red is third order, so it's the target. We have to degrade internally because of some ill condition of the MLS matrix in this region in green here, where we have only second order. Also close to the free surface, where we have to degrade to zeroth order, and close to the wall also we have to degrade. And that's the difficulties of this approach. The condition of the MLS matrix is very delicate, and to maintain stability, we have to degrade the order of the MLS reconstructions. And again, we have to sacrifice global conservation for the benefit of higher consistency. Okay, going to the applications. Our daily business in the Pelton design is making use of this process. So based on an SPH-ALE simulation of the flow in a rotating buckets, we characterize the hydraulic performance of the Pelton buckets, but we also extract the pressure loads on the rotating buckets, and we inject that in a finite element solver to compute the stresses. And this is really done on a daily basis in our company. Okay, more interesting. So we are able now to simulate casing flows. Here is the example of a horizontal axis Pelton turbine in its casing with two jets. The particles, they are colored by their velocity in the absolute frame of reference. So red is high velocity and blue is low velocity. And what is of interest in this case is that we managed to track those water sheets on a long distance till they impact the casing walls. And this is very important for the design. A similar example, but with vertical shaft. Okay, so it's not symmetric now. We have to simulate both sides of the runner. But here again, we can see how the water is evacuated by the casing walls. Here is an example which involves a dynamic behavior. So it's the case of a startup of a Pelton turbine. So we start with a Pelton runner, which is initially at rest. We represent only 1/2 of the runner. And we have a water jet that is gradually increased in terms of its diameter to mimic the gradual opening of the injectors. And the rotation speed of the runner is computed by the solver according what is the driving hydraulic torque, and a certain analytical model as a resistive torque that represents friction, possibly electrical torque also on the machine. And here we monitor the runner speed, the discharge, so they are increasing step by step. And here is the torque, where we can see each interactions between buckets and jet, those spikes, and they become more and more frequent, which is the sign that the runner accelerates, of course. And based on that, was possible to compute the stresses in the buckets, which is because the startup is a very demanding phase. Here's another example. The target was to provide a virtual test bench for a regulation algorithm aiming at finding a stable position for this device, which is a deflector, in case the runner is suddenly disconnected from the grid. Usually we go to runaway speed, and that's why there is a protection to immediately deviate the jet. But the target here was to maintain the runner rotation speed at synchronized speed, because the customer was interested to restart power production as soon as the grid becomes available again. And so the runner rotation is again a balance between the small torque that is obtained from this deviated jet and a certain resistive torque. And we can see that finally, the regulation algorithm managed to find a stable position for the deflector, and we maintain the runner rotation speed to nominal speed. Okay, an example with confined flows. It's the startup of a Francis turbine. So here is the velocity in the domain. Here is the pressure on the runner, and here is a zoom on the particles around the guide vanes. So we have a cycle of guide vanes which is originally closed, and we impose a total pressure at the inlet around the domain, and at the outlet we impose a pressure, an outlet pressure. And when we open the guide vanes, the flow starts, and the runner again starts to rotate because the solver solves its equation of motion. And here again, the target for us was to get the hydraulic loads on the runner, because again, the startup is very demanding. So here you see an example of application for confined flows, where SPH is interesting because it can very easily manage the deforming computational domain around the guide vanes. A final application. This is what we call an hydraulic torque converter. So it's kind of hydraulic clutch. We have two shafts. Shaft one, let's call it like that, is connected to a pump, and the pump is this runner here. So from this point to this point, this is a pump. It will receive a liquid from above, and it will send it horizontally in a second machine, which is a turbine, and the turbine is connected to a second shaft. So the idea here is to transfer the torque from shaft 1 to shaft 2 using interactions between the pump and the turbine. And pumps and turbine, they belong to a sort of closed loop that is here. So out of the turbine, the liquid will move upward, go through those guide vanes. Again here, a second cascade of guide vanes, and re-enter the pump. But originally, it's full of air, not of liquid. And what is interesting with SPH is to simulate the filling process and the startup of all these. So we start with shaft 1, which rotates at a certain speed. So the pump rotates in air, and we do not send any energy to the turbine. So the turbine and shaft number 2, they are at rest. We inject an oil, a liquid, from those two inlets here. We fill the upper chamber, and when the upper chamber is full, so there is a pressure established, we start to really push the liquid in the pump, and the pump provides energy to this liquid, but for the moment it's a kind of free surface flow in the pump, and the liquid goes across the turbine, and you see the turbine starts to rotate, but we also start to feel the closed loop here. But for the moment, we still have a free surface flow in the pump, and most probably also in most of the turbine. But it starts to be filled with liquid. And now, very soon, we will start to fill completely the closed loop, and we will instead of having a free surface flow, we will have a confined flow in the pump and then in the turbine. And now we really start to transfer a lot of energy from the pump to the turbine. So the acceleration of the second shaft becomes very, very important. At some point, everything is full with liquid. So the inlet section, they do not deliver new liquid particles anymore. We have an established recirculation in a closed loop here. And we go on accelerating on the second shaft till we reach a synchronized speed. So that's an hydraulic clutch. Okay, quick conclusion. It's only one slide. Sorry, Angelo. Well, as a conclusion from our point of view, with SPH-ALE, we have a very stable and versatile tool for various applications in hydraulic turbines, and not only for free surface flows. You have seen examples of applications in confined flows, especially with deforming simulation domains. But also SPH-ALE provides clear evidence of the main problems, I would say, of SPH. For me, if we look at Eulerian simulations, which are very easy to perform with ALE formulation, in fact, we have results competing quite well with finite volume results. I don't say in terms of competing in terms of computational time, but it's in terms of quality of the results. They are kind of similar. But all the problems we have, they really start when we start moving the particles, especially with a Lagrangian particle motion, because then the particle distribution becomes disordered. We have little control on what happens. And at minimum, we have to impose this correction of closed box error if we can. For us, the combination of SPH with other methods, like the finite volumes in our case, is really a key, because SPH cannot be good at everything. It should be restricted to flow regions where it is the best choice. Otherwise, it should work in combination with other techniques elsewhere in the domain. What we work on, and the directions of improvements from our point of view, are the particle shifting to maintain a better control on the particle distribution. Particle refinement, we are, well, it's a key, especially for geometrical details of the components we put in the simulation domain. Also, a problem that I think 99% of SPH implementations neglect is what I call the visibility criteria for the neighbor search. A very simple illustration is here. If we have a very thin obstacle that is less than the particle, the kernel support, here we have the red arrows, which are taken as valid links in our neighbor search, but I think they are not valid links. And in mesh-based techniques, they would never be taken as valid links, of course. So here, in fact, if we consider these as two separate tanks, we would have one tank interacting the other while we have a vacuum in between. And this, I do not have a solution, but I know that in some of our applications, this triggers issues. And finally, time integration. Well, we have this explicit time integration that is governed by a CFL condition, but the CFL condition is governed by the acoustic speed of sound, which is of no interest for our applications. So works on time integration is probably, I think, a very important next step to increase the interest of SPH for industrial applications. Angelo, sorry, I'm late, but I'm done.
All right, thank you, Jean-Christophe. No need to apologize, actually. Thank you for this brilliant presentation. It was a really great overview of the SPH-ALE formulation, and it was also very interesting to see its application to real, industrial problems.